Okay, so I think we are ready for the stage. Ladies and gentlemen, please give a warm welcome to Dr. Stefan Poslad.
Hello everybody, it's great to be at your great university again. I was here last about 10 years ago and everything's still as wonderful as it was then. Wonderful location, climate, food, etc. Right, so I've been working in AI for about 20 years and I'm just going to give some reflections and some thoughts about AI and a different direction that it could be heading. So the title of my talk is, in an age of some recent successful big data AI apps, is there still a case for utilizing small data-driven distributed AI? Here's an outline of my talk. It's basically in about 4 parts. I'm going to give some preliminary background information about AI. So I'm going to talk about architectures, etc. I was going to say a bit about human intelligence versus artificial intelligence, but I'm going to skip that. I'm going to mention 3 kind of applications and the AI challenges of them. And they are to do with travel. Then I'm going to talk a little bit about some methods for small data AI. And then I'm going to give conclusions and future outlook. Right. So, what is the motivation for small versus big AI? So, compared to past models, design advances, what's making the most recent advances appear to be so successful? And by successful, they seem to be better at classifying different kinds of data in different kinds of application domain, right? So, and by big data, we also associate with that with big computation, right? Big network bandwidth, and this is dominating some recent AI model successes. So for example, right, we have this chatbot, GPT-3, this answers text queries and can generate very sensible answers. We've got AlphaFold, which can predict protein structures, help us to understand diseases, design new drugs. We've got Waymo and Tesla, who've made sort of significant progress in advancing the use of autonomous vehicles. We've got DeepMind and AlphaGo, and this seemed to beat the world's best Go player at the time, and he was very impressed by it, so he actually seemed to retire. But is the way, right, these new AI models and the way that they resource and the way that they scale up, becoming less inclusive for some major world regions and some specific types of stakeholders? Because not all of us have access to these huge computation and data resources that are behind these AI successes. Is there a way that we can complement or combat this with small data AI? So one of the things to think about is, what do we mean by big when we say big data AI? So I notice also to collect big data, right, it can be very time consuming. First of all, you have to set up and design a system, right? And then secondly, you have to operate it to collect sufficient data. So both of those have a significant time. So AlphaGo, right, was initially trained from 30 million moves. And if one move takes 2 seconds, and this is of experts player, right, moves, and this data was in the public domain, right? So it was accessible to them and accessible to all of us. So not all data is like that. If we look at the data input, right, and if we see a typical game is 500 moves per game, and then say we record one move in 3 bytes, right? We've got the X coordinate on the board, the Y coordinate on the board, and we've got the ID of the player, right? Of the 2 players, right? And so if we do like a rough calculation, right, for all of those games, right, we get something like 45 gigabytes. In addition to that, what we could do, right, is that we could add the temporary data storage, right, to this as well, because the way that AlphaGo is working, it's doing multiple searches at the same time to try and decide what was the most successful search strategy, right? So in one of the last versions, there were like 64 different search threads. So if we add that, then we have something like 3 terabytes, right, of data being generated, at least temporary data, to like work out what the best strategy is. So the computation design of one of the early versions, at least, right, was that it started off with 12 search threads, right? There were more later on. There were 428 CPUs, right? Then there were 24 specialized graphical processing units, which Google has a particular name for their hardware called a tensor processing unit. And so there were 64 of those, and then that gave a kind of expert level rating, right, for the skill of the player, the expertise of the player, and it was like rated 3,000, right, whatever that means. And in 2019, right, this one of these TPUs, right, could do 45 teraflops, right, which is like, and 1 teraflop is like 1,000 to the power of 4 floating point operations per second, right? So it's an amazingly fast hardware. After the initial training, right, what happened also to this kind of neural network architecture was that it was also set to play against different instances of itself, right, in a large number of games. And it's unclear what is meant by a large number of games, right? And there was a particular AI technique, a learning technique, reinforcement learning used for that. And this further improved play. And then at the end, because the network was fully trained, right, you could like run it on a kind of less powerful hardware. So the hardware that you could actually operate it on, right, you could operate it on a 4 TPU hardware, right? But it did use a pre-trained network from the early training and this kind of much bigger hardware. Right, so coming back. So that's just an example, right, of what the resources were needed, right, to be able to be the kind of best Go game player. So there is this definition of big data, if we look at this a different way, right, called the 3V definition from Delaney, and this talks about volume, velocity, and variety of data, and there's actually a 4th V which came later. But there's no universal domain independent quantity to define big, right? It's hard to say, is it more than 1 million, is it more than 10 million? We don't know. And then the other thing is that, we're just talking a little bit about big data storage now, rather than data processing, which we just talked about for Go, and we're just going to ignore data networking. Okay, so one rule of thumb to kind of try to decide whether it's like big data is, can the data be processed and handled, right, in a typical PC? And then the issue now is with PCs is they're becoming more powerful, right? We've got quad-core, we've got 8-core system on a chip CPUs. The Apple chip is like amazing. It's like a completely different design as well. And if we look at OpenAI, right, which developed ChatGPT, it estimates, right, that AI training measured in the number of petaflops, right, floating point operations per day, right, is doubling every 3.5 months, right, since 2012, okay? And this is much faster, right, than Moore's hardware chip law design. And also the hardware cost is also falling. So we can say that a petaflop per day, the number of petaflops per day is about like 10 to the 15 neural net operations, right, per second for one day. And then we get like these 10 to 20 operations, which is this petaflop day count. So, and then if we like we can now do it like a calculation, right? So if we rented some computation, say from Amazon, right? The calculation would come to that it would cost, right, about £250,000, right, of time on the GPUs, right, to actually be able to build and train the network, right, to kind of compete and beat the best Go player, right? And then it's interesting, like in 2023, one of the chip manufacturers, AMD, like released this chip, this RX 7600, and this has got this like impressive kind of peak performance. And that chip, right, just costs $270, okay? And then if we look at how many of these like terafloating point operations per day it could actually run, then it's doing about 2 exa floating point operations per day. So, it's pretty impressive what some relatively low-cost hardware can do. And one of the other questions we can ask is, if we have a smaller data set, right, is it useful and is it representative of a larger data set? So, one of the interesting things is if you do human-computer interaction and you look at the kind of ratings and the classifications by 5 users, right, you can pick up 80% of the design issues of a user interface, right, this is kind of like a magic number. And then there's like another magic number of like 40. So if you've got 40 good users, generally, that's considered to be kind of like representative of the variation in the population at large. And then 100 users give you kind of more nuanced information to look at the differences between users. Right, so now coming back to these like V's, right? So we've got data volume, we've got the data variety, right? So the data variety could be to do with the mode of data, like is it images, is it like text, and then how do you represent that? What kind of image, how is the text represented? And then we've got the velocity, right? So how many measurements, how often is like new data, is the data being changed? And then the other thing that we can ask ourselves is, what does the data mean and how accurate is it and how truthful is it, right? So we can call that veracity, which wasn't in the original 3V definition, right? So if we look at computer vision, right, which is being used in autonomous vehicles, right, we can say that that's at the top of being big volume, big veracity, big variety, big velocity, right? And if we look at Chat GPT, we can say that the kind of the data, its volume itself is like lower, the variety is lower, the volume is lower, and the velocity of new data being generated is lower. If we look at motion environment sensing, so environment sensing could be once a minute, could be once every 10 minutes. Motion sensing could be quicker, could be 30 hertz, could be more. We can see that we've got like this kind of velocity down here. And then there's like 2 more examples here. So for example, if we look at health applications, so health applications is going to like combine computer vision with chatting, maybe a doctor consultation, and then with sensing, sensing your blood pressure, etc. We can put the health up there, right? So it's lower than computer vision because there's less vision here, right? We're taking less images and we're not videoing the patient the entire time, okay? And then the last thing is if we look at Go and we look at machine learning play, okay, then that's right down there at the bottom. So I've got references at the end, and I circulate the slides, right? But this kind of recent report by OECD, has come up with these figures to kind of quantify data. So it's very large. It's saying an exabyte or larger in terms of the data. Large is like petabytes. Medium is gigabytes, and sort of small is like tens of gigabytes or less, right? And I didn't put any axis on here, but if I did, right, for volume, I would put at the top, 10 exabytes. For velocity, I would put like 1,000 gigabytes. And then these other two things like data variety and data veracity, right, they're hard to quantify in terms of units, right? And there's no agreement, and it would be domain dependent. Right, so this is like the simple model of an AI system, right? We have the intelligent system or AI system, right, which is taking data in from the sensors. Then that data is being used to build a model of something specific to some task, and it's an AI model. And then the outcomes of this like AI model is to try and affect the environment, make some decisions, perhaps classify something, personalize something, recognize something, detect something, etc. Okay. One of the interesting things here is to think that the environment is just not as simple as just like one environment. So we've got like the physical environment that we're trying to interact with. That's very important. We've also got a human environment, right? So humans are involved in using the system, and it's affecting human behavior and things like that. And then the third thing is we've got a digital environment, and we tried to quantify what resources we need from this digital environment, right, to do AI. Okay, so we've talked about the number of like flops per day for some like calculations, and we've talked about the data storage that we need, and we've talked about the temporary data storage. So let's look at like an intelligent environment, right? So we walk towards the door, and the door opens, right? So we could say that that's a kind of like passive environment, right? Another thing that we can think about is that what if this environment's a bit more intelligent? So what frequently happens when we walk towards the door and we walk past it but don't go in, right? The door opens in any case, right? What is not, it's a waste of energy, right? And it's a lack of security. Another problem you might have is if you have a disabled user, right, that wants to go through the door, you'd like the door to stay open for longer, right? So you want this to be more adaptive here. You want the environment to be more intelligent. So now we're talking about that we've got an intelligent environment here, right? Not just a passive environment, okay? And that's going to make the interaction more complicated to interact with. If we look at like the life cycle, so we have to define the problem in terms of tasks. We have to prepare the data, acquire it, clean it, transform it so we can process it. Then we, from the data that we're processing, we build this model of the world in order to interact with it, to affect it. We have to train it, and we have to test the model. Then we actually deploy and use the model for some applications purposes, okay? And then we like monitor and optimize it, and if we find that we can improve it, we could change the problem definition, and we could change lots of things here, okay? And we can create a smaller data model by optimizing any one of these like different stages of this life cycle. And here's some examples of typical AI tasks, right? They're to recognize, classify things, detect events, forecast, personalization, etc. Right, so some typical like AI design issues that we have to think about is where does the data come from, right? Is it humans, is it machines, is it both? What about the data veracity, right? How accurate the data is? Is it from experts? Is it from standard regulated, calibrated devices, point of sale transactions, systems? Is it from observing machine sensor behavior? Is it synthetic data, or is it derived data? Another thing is, where does this data like reside so we can access it, right? You know, is it like public? Is it in a private company, so you have to be registered and pay to use it? Does it also hold personal data? And then in terms of the variety of data, is it unstructured, semi-structured, etc.? Okay? And in terms of the data format, right, there are like standard formats, non-standard formats, and then there are also formats for metadata, right? So the metadata helps us understand the data. So if we just process the data without the metadata, it probably wouldn't be that useful, okay? And then the AI model could be a single AI model, but lots of AI models, particularly in computer vision, they're composite models, right? They use a pipeline of different models to do different parts of this kind of application tasks. Generally, one thing is a lot of the AI models that are built, right, are specific, right? They're making assumptions about a domain, they're tuned to the domain, and they're biased to the domain, versus, right, a general AI, right? Artificial General Intelligence, or AGI. And then in terms of model devices, right, one way we could just divide them is we could say, you know, are they symbolic in terms of like logic rules or like ontologies, if you understand what they are, or are they statistical? So in general, statistical, like standard deviation, that kind of stuff, but also in terms of like genetic algorithms, artificial neural networks, and machine learning, right? We could call all of that like statistical data techniques, group it like crudely like that. And we can, of course, combine those two, right? And then the last thing to think about is the data model, right? The meaning of it for a particular purpose, you know, is that from supervised data, so we have the metadata to say that this class represents this. Is it unsupervised? Is it semi-supervised, which combines both, okay? Or is it like reinforcement, or is it like human, you know, expert knowledge, right? So we've got all of these different choices we can make that affect the AI model, how it's built, okay, and how it's used. Right. This last thing about environment types, I'll just like summarize briefly because I think that I am taking quite a time. So it's worth thinking, right, that we also have to also understand the environment, right? Not just the task being done. We also have to take into account the environment in which the task is being done, right? So, you know, so here I've got these antonyms, which are just the opposite of these types of environment. So, you know, is the environment partially observable? So, you know, an example of a partially observable environment would be you've got like a computer vision camera, right? And there's some obstacle in the line of sight to the object you're trying to recognize, right? And we might see part of the object part of the time, and we might see all of the object part of the time, right? So it's partially observable. So that's an example. We've got other like environments which are like non-deterministic. So, I mean, we talk about the weather in the UK a lot, so that's a good example of non-deterministic. Then we've got like sequential systems, so, you know, just time series systems. We've got environments that change a dynamic. We've got environments that like are continuous, and we've got environments that are active. And then, like, if we look at these sequential environments, we could say that there are different types of AI model that we could like pick to look at them, right? So we've got like recurrent neural networks, convolutional one, and this long short-term memory one, and they have like different properties and different complexities, which I'm not going to go into. And so, you know, different AI models, just to summarize, are going to be more effective for specific types of environment and for specific tasks. And the challenge is, right, to decide which AI model is suitable. And basically, I can say there are three ways you choose the AI model, right? You look at what's currently being used as the best state of the art, right? Another way to look at it is what is the characteristics of the problem, okay, and then use that to select the method. And then the third thing you could do is to consult somebody, you know, an expert, and get some, you know, advice on how to choose a type of AI model. Right, this term, a foundational model, I think it's been coined by Stanford, and basically it just means that you collect a huge amount of data from a huge group of users, and you do a huge amount of processing on it, and a lot of it is the statistical kind of neural network learning, and this is the typical architecture, right? It's in the cloud somewhere, and there's some access to devices to feed the data into it, so it can be processed, and also to access it for humans to make decisions about. And then we've got edge computing. So in edge computing, right, the devices close to where the data is being generated, they do some computation as well. Okay, so we've got that option as well to look at. Right, so now I'm going to start talking about 3 problems, right, that AI can be applied to. So this is like one project I did about 10 years ago, and I'm just hoping, right, that the video and the audio is going to play. It takes a few seconds. Right, so to just make a few comments about that particular action, right? So, that application, excuse me. So, we can say that some of the jobs of the AI were to classify the transport modes which human travelers were using, okay? Another thing we did was we tried to gamify it, right? So if you used favorable, eco-friendly transport modes, then you'd have more points, right? And then the other thing we tried to do is give people incentives, right, to change their behavior, right? So one incentive was, that you're higher your point score, you were a great sort of player, and that drove, that made some people change the behavior. Another thing that kind of made people change the behavior was that information, right, is a great incentive. So generally, psychologically, the more information people have and the more educated somebody is, that they make better informed decisions, right? And then the actual other thing that we did is we gave people a physical reward, like a nice apple pie, right, if they used a particular transport mode. Now, if we like automated this using artificial intelligence, right, what would have happened with this is that everybody should have like switched to more walking, more cycling, right, some public transport, and hardly any private car use, right? That's what would have happened with a complete AI system. But this would not have been optimal for some types of user, right? So some people, right, were doing, in their journey in the morning, right, they were taking their children to school and then driving to work, right? Now, can you imagine what the time cost would be if you did like public transport, right? You might be lucky, the bus goes along to the school, and the same bus, then you can catch further along the route to your workplace. But that hardly ever happened, and that was one reason why some users never switched when doing their daily traveling, right, from using, a private vehicle, right? It just didn't happen. Right, I'm not going to play another scenario, and I'm going to ask questions later, so pay attention.
Vas tarde. Apúrate si quieres una buena calificación.
Voy lo más rápido que puedo.
¿Has pensado en correr? Es saludable y eficiente.
Seguro que no hay más trabajos disponibles. Yo estudié para ser profesora y estoy haciendo mercados.
Y además puedes quedarte con los puntos de fidelización. Eres una monje afortunada. Tienes que confiar en la aplicación. ¿Te sientes inspirada? Gracias. Chao.
¿Quién soy yo? No, eso no es lo que quiero decir. ¿Para dónde voy? No. Puedo volver a empezar. Olvídalo.
Estoy presente ahora. Me amo. Estoy libre de mi ira. Estoy libre de mi tristeza. El amor es mi esperanza.
Habla español. Adiós. Olá, me llamo María.
Bueno. Hola otra vez. Ay, no, cállate. ¿Qué está pasando?
Buen día, Emilio. ¿Qué puedo hacer por usted?
¿Qué está pasando? Mis puntos están bien.
No se preocupe, sus puntos están seguros conmigo. ¿Le puedo ayudar en algo más, Emilio?
Yo no soy Emilio, yo soy Juliana Restrepo.
Por favor, espere.
Hola, Juliana Restrepo. Me alegra verte. ¿Qué puedo hacer por ti?
Mis puntos están bien. ¿Qué está pasando?
Tranquila, todo está bien. Parece que alguien está intentando vulnerar su cuenta. Por favor, espere mientras reinicio su dispositivo. Hola, Juliana. Me alegra verte. Hoy te ves hermosa. ¿Estás estrenando zapatos?
Ya lo arreglaron. Tengo que seguir trabajando.
Estoy trabajando en eso, pero necesito verificar tu información biométrica. Por favor, sigue la línea azul hasta el centro de servicio más cercano para confirmar tu identidad.
Sí, pero mis puntos están bien.
Todo está bien. Chao.
¿Qué? ¿Qué es esto? ¿Qué? ¿Qué está pasando? No, mis puntos, mis puntos. ¿Qué hago? ¿Qué hago? ¿Qué es eso?
Right, so I'm going to stop it there. And one of the questions to think about is like, when is this, right? Is this now? Is it like 5 years' time? Is it like 10 years' time? Did anybody notice about the bus, right? Was the bus autonomous or not, right? So that would give us a clue when in the future it could be perhaps. In actual fact, there was a bus driver, and it could have been autonomous, but maybe in the future we want people to do jobs that they enjoy. So although the bus could be autonomous, we still have a bus driver, right? We've decided to accept that cost to do. And then in this particular future, right, there's no money, right? There's only like kind of, meta world points, right, that act as like currency for accessing different services, right? That's the way that goes. And this person's not very happy with their job, right? They're a personal shopper for somebody, and they have to go into the supermarket, buy all of these products, for the pet dog and things like that. And they keep trying to look at their status to see, if they've got enough points that they can do something else, right? And then another thing that happens is that there seems to be like some network problem in that they're unsure, right, about if their points are really linked to their identity or not. And then right at the end, what happens is the points are linked to an identity, like through biometrics, right? And then somebody bumps into her, right, steals some blood, and then manages to like clone the DNA from her, and then uses that, right, to steal her points and to kind of change her identity, right? So she's lost everything, right? She's lost all of her points because somebody took a blood sample from her finger that bumped into her, right? And then, in terms of the AI there, you can see there's like a huge amount of like computer vision, to support augmented reality as well. There was a lot of like physical world interaction, like context, tagging. The environment was like really, really smart everywhere. The clearing of the road. If people were on the road and traffic was blocked and then traffic was allowed there. So a huge amount of like AI there. The last thing I would just want to talk about is this is this like, yeah. I just want to talk about a very simple autonomous vehicle problem, right? So we've got like 4 traffic lights, we've got some vehicles, and now the question is, how does the vehicle, right, identify the right traffic light, right? So we can obviously detect the colors, but if we're like a taxi here, right, you know, how do we know this is the right one and that's the wrong one, right? Or vice versa, right? And not these ones here, right? So just being able to kind of like do object recognition of lights, right, is not enough. We need to recognize the right light, okay? And so there are many challenges here, right? So, you know, is the traffic control the lights, right? Or are the traffic lights sending data, right? Saying stop, go, you know, prepare to stop, right? You know, and another thing to ask ourselves is it illegal to drive through a red light, right? In most cases it is, but in some cases it's not, because if I have a green light here, right, and I go forward, and I'm going to turn right, right, I'm going to have to go through a red light, right? But I have to ignore it, right? And how do I decide, how does the car decide to do that, right? And then another thing that can happen is the red lights can also be from other vehicles, right, that are braking, so you have to see that red light there as well. So it's kind of more complicated, right? And then the other thing robbers could do is they could put a red light there and cause the car to stop and try and hijack it, right? So it's not a different, you know, it's not an easy problem, even for computer vision. And if you look at some of the latest research, so these references are at the end. There's this paper by Vetus in 2020, which is using this kind of LISA traffic light data set, and the problems highlighted here, right, don't appear to be in this data set. So it's not really that realistic, I would say. So, you know, those are like the 3 applications with, you know, AI use can be used in them, but it's still challenging to use AI effectively and accurately in there, right? So coming to small AI designs, and now I'm going to like start to kind of move towards the end, we could say that what we could do is just use smaller data sets, right? So we have smaller data footprints, and in this analogy here, right, is we've got an acorn, and then that, like, from the acorn, you know, it grows into like a tree, right? The second thing we could do is data reduction. So this is like symbolized here by compressing, you know, some pages, okay? And we could do that digitally. Another thing we could do is we need more users, and we don't have enough of people who are colleagues, right? We could try and enlist the public using like crowd sensing or citizen sensing, and then share the data with them as an incentive to help make some decisions which are you know, common to them, right? Another thing we can do is we can do like noise reduction, so we can make the data smaller because we're just going to remove some of the data which is not useful, is varying too much or is not varying, you know, at all. And you know, small AI models can achieve amazing results because a lot of people who have applied sort of ant colony algorithms and sort of watching how bees find their way to flowers, you know, they are remarkably resilient routing algorithms from a much smaller kind of intelligence and intelligence model than humans have. Another thing that we can have as an AI design is that we can like employ AI in devices which are closer to where the data is being produced and to where the data is being accessed. And the last thing we can do is like AI chips. So a lot of smartphones have AI chips in them. I really like my Mac, right? This has got this M2 chip in there. And what's really smart about this M1 chip, which Apple were the first to do this, right? So it's a system on a chip, but it's got multiple different types of hardware chip on the same chip, right? So it's got a GPU on the system on a chip. It's got a DSP chip, on the same chip as well as the CPU, etc. And that actually makes a lot of tasks faster than if you had a much faster CPU or even a GPU, right? That combination of different hardware, right, on one chip is much faster, okay? So some challenges if you have a small data set, right, is that if you want to classify if something's like abnormal, right, in the data set, you only have a small set of abnormalities and you have a large set of normal classes, right? And it makes it like quite unbalanced in order to do a classification. Basically, there's not enough abnormal events. So we've got like two strategies we could use here with this small data set. So one strategy is that we could generate artificially, right, more abnormalities, right? So we're generating artificially more abnormalities, right? We could do that, right? Now, a completely alternative technique to that would be that we've got real abnormalities, right? And what we're going to do, we're going to vary them, right? So we add like noise to them, we increase part of it, we decrease other parts of it, okay? And that's like another way that we can have assembled a kind of equivalent number of different classes to kind of balance the classification better. So we could do that. Another thing we can do like is data reduction. So we can do like data compression, binning, filtering. We can like measure just enough data samples in order to record changes and not sample too fast. We could do that. Another thing we could do is we can look at classifying and processing features relevant to the task and the application rather than the raw data, right? And then we would have a smaller data input set in order to run our kind of AI model on. Okay, and that would reduce data storage, processing, transfer. And as we said, we could do data enlargement if we more users. We could try and enlist users by trying to share some like data outcomes with them. Another thing we can do to reduce data noise is like outlier identification, etc. I'll give some examples of these later. Small machine learning could be non-deep learning, right? Sometimes, perhaps in many cases, right, these simpler non-deep learning algorithms, right, seem to be as accurate as classifying as other algorithms. And then even if we use deep learning, right, we've got a number of techniques, right, that we can do to either train the network for a new application. We could take a trained network from one application domain and check whether we could use that trained network in a different application, okay? Maybe they're related somehow. Another thing we could do is we could do like what's called federated machine learning. So basically, we have a different machine model, right, in different domains. And one good example of this would be like global autonomous vehicles, right? So if, for example, I designed an autonomous vehicle for California, US, right, that would not work very well here in Bangkok, right? It would not work very well in Mumbai, right? And it might not work very well, in London because the streets are very narrow and there's just a different road design. So we would just build a different AI model, a kind of edge model for each different region, right? And and tune the model there and keep the data there, right? Other things we could do is like what's called zero shot, single shot, or few shot learning, which I'm not going to go into, and distributed edge IoT systems. I've got some references, but I'm not going to describe that either. And I've talked a little bit about specialized AI chips. And then here are just some examples of different things. So one of the things that we could just do, right, in this kind of first transport mode recognition project is we could just look at speed, right, and use that to try and classify the transport mode. So, if it's less than 2 0.2 meters per second, they're stationary, right? If they're 1.3 plus or minus 0.2, they're like walking. And then, if they're this range, they're cycling, right, as an example. And then if they go that range, right, it's a bus or it's a motorized vehicle, okay? Could be a motorbike. And then the thing that we know there is we collect our data set, right, just in non-congested environment, right? Then in a congested environment, we're going to have this so-called overfitting and this bias, right? So we've biased the model to free-flowing traffic, and the classification works there. But when the environment's changed, right, that same trained model makes the wrong classification, right? So what we need to do there is to increase, our kind of data set to take into account this congested, environment as well. And there are different classifiers which you could use there as well as neural networks. I mean, another like example I'm talking about is like step counting and then working out the distance you move by the number of steps you take and the number of turns you make, right? And this could be used for like human simultaneous location and mapping applications, right? So let me just check time. There's like a particular algorithms for this which I could describe, but I'm just going to skip, which they're in the slide. But basically, the algorithm is that you estimate the step, right? And you could do that using a static algorithm based upon a person's height that's related to your step size, okay? Then all we need to do with the application is be able to detect steps and count them, right? And then we could get the distance moved if we multiply by the step length. And then the other thing we could do is to look at the distance from one point to another point we're moving, is we could just look at the number of changes in direction, right? And all of that together, right, gives us a distance we've kind of moved and changing direction. And then we could say that we could use a combination of sensors to do this, right? If we look at the data, so this is like accelerometer data, we can see that we see these peaks. And another thing that we can see is these peaks are not all the same height, right? Some of them have deeper deceleration, some of them have higher acceleration. So there's a lot of variability even in one person just walking, okay? We're not robots. So another thing to think about is how can we reduce the data analysis, right? And the kind of like AI model. So one thing that we notice, right, is if we just sample about 4 times a second, and we sample for a time window of 2 seconds, so we make 8 measurements, right, we can detect enough peaks and troughs, right, in that 2-second window, okay? And so we can step count if we measure slower, right? This is for walking. Of course, if somebody was sprinting, right, this method wouldn't work, okay? We would need to sample faster. So that's just an example of kind of small data processing that we could do. This is just an example of how we could calculate the direction changes by, looking at the compass and or the gyroscope. I'm not going to go into the details about that. Another technique which I've looked a lot at is like people profiling indoors. Okay, and typically what happens there is we have like a number of transmitters, which are like Wi-Fi transmitters, and we look at the receivers. And the thing that you notice, right, is that the receivers have a different signal strength from the transmitter depending on which one is nearest, right? So for R1 receiver, the T1 should be the highest signal strength, then T2, then D3, and it would be a different ranking for R2. And then there are lots of benefits of doing this simple processing as looking at the ranking rather than the values. Because the other thing you find is that the received signal strength depends on the electronics which differs in the receiver, right? So different phones will measure different radio frequency received strengths, right? That's another issue. Let me go through and just point another thing. So another point is like, in some parts of our university, right, there are 100 Wi-Fi access points, right? So we could use all of those and rank them, right, to determine the position, right? But one of the things to bear in mind is that not all of the access points are have good quality data, right? Some of them are very noisy. So the access points to avoid, right, are the ones on doorways, right? Because they always have a very, very variable signals as people kind of move in and out past them, right? So if you spot noisy sources of data, right, the best thing is to identify them and just like discard them, right? So that's a good technique to have improved the data quality. This paper I did in 2014 received the prize as the best paper in the IEEE Census Journal and had a lovely $2,000 cash prize as well, so it was nice winning it. And what we did there was look at what features from combining walking and looking at GNS signals, right, we could classify, and what classifiers we could give, right, and where we would put how many sensors to give us the best classification, right? And we eventually saw, right, that if we just use 2 sensors and we use a particular set of features and a particular set of classifiers, then if we use more sensors and we use other classifiers, it didn't improve the accuracy, right? So that was what we did there. So this is now coming to the end. Just a couple more slides here. So future challenges. So a challenge is that generally we're better at building AI models of a specific domain, and we're still not very good at generalizing them. So we're still not very good at AGI, right? Although we're getting better. Another thing that's going to happen is heterogeneous AI models, right? Is what happens when we have smarter things developed by different vendors and somehow they interoperate, right? That is an unresolved problem. Another thing, as I said, is small AI is still there. And there are huge opportunities, right, for companies and startups. And this is my final slide. So we've got Thailand, AI opportunities and challenges. And then the last thing is there's 2 things I looked at, which was the Thailand 4.0, which was like an industrial 4.0, which was developed by the Germans, and lots of countries have applied them. So, Thailand's identified all of these particular sectors, right, where they think are going to grow, particularly through AI. And then the other thing I looked at, right, is the Thailand National AI Strategy and Action Plan for 2022 to 2027, but there wasn't very much detail for that. And that is the end of my talk. Thanks very much for listening. And, as there are no questions, goodbye and thank you very much.
No. Thank you very much. Are there any questions for Dr. Poslad?
Any questions? Oh, yes, please. Oh, we have the microphone.
Let's have the microphone.
ขอให้ช่วยแปลให้นิดหนึ่งแล้วก็แล้วกันนะฮะในตอนเริ่มต้นท่านอาจารย์ผู้บรรยายได้กล่าวถึงว่าสไลด์ที่เตรียมมาเนี่ยก็มีมากแล้วก็เวลามีน้อยส่วนหนึ่งที่สไลด์ที่เตรียมมา มีอยู่หัวข้อหนึ่งที่ท่านลบออกไปก็คือ Human Intelligence and Human versus Machine Sensing and Actuation เนี่ยเราจะสามารถติดตามข้อมูลนี้หรือว่าไปเรียนรู้ได้จากช่องทางใดบ้างนะฮะ
Right. His Holiness want to know there's one slide that you sort of skip over in the beginning about human intelligence and human sensing. Can we follow that? How can we find out more about that?
You can. You can, right? I just ran out of time, right? So there was somebody whose name I forget, right? Which said, right, there are at least 8 different types of human intelligence, and a lot of artificial intelligent machines, models, just like focus on only very few of these intelligence. So one of the intelligence is like verbal reasoning, right? So a lot of AI systems try and support that, and they do that very, very well. So that's one example. But other types of intelligence which humans have are things like kinetic intelligence, so motion intelligence. There's also like social intelligence. There's music intelligence, and there are other ones there. So when I share the slide pack, I will add a few more slides in the appendix with some information and some references to look at that and like an analysis of humans are still very much better at so many other types of intelligence than machines are. Machines are only good at like a few types of human intelligence. But thanks very much for your question.
Thank you very much, Professor. Appreciate it. Thank you very much.
Right, soเดี๋ยวอาจารย์จะแชร์สไลด์ให้พระคุณเจ้านะคะ
Do you have any other questions? Oh, please. Oh, right there. Yes.
Okay.
Could you please tell your name and where you're from?
Sorry.
Yes.
My name is Rattapul Maranusat. I'm a lecturer here in Naresuan University. The question is, nowadays people talk a lot about deep learning. So in your opinion, and in your slide, it's quite clear that the old method of feature engineering, or what we call shallow learning, are not going to die soon, anytime soon.
Yeah, I agree. So there are certain kinds of problems, right? For example, computer vision related, where these like complicated neural network models, right, have been shown to be better at like classification and recognition. But other types of application tasks, such as like detecting ECG abnormalities. I have a PhD student, and we've looked at deep neural networks versus other machine learning techniques, and these other machine learning techniques work as well, if not better, as the deep learning neural networks. And the other thing you could argue is like, so there's like shallow one-layer neural networks, then you've got the deep neural network with multiple hidden layers, right? That's the second generation one. And then you could say, why don't we use the third generation neural network, right? Which are these spiked neural networks. And are they better? The issue at the moment for most of us researchers is there isn't a lot of like good software libraries to make us easy to like experiment with them at the moment. But I think for a lot of application domains, non-deep learning methods, machine learning methods seem to be as effective, if not better, than deep learning methods. But thanks for your question.
Thank you very much.
Thank you very much. Do we have any other questions or comments? Oh, at the back right there, over there.
Thank you for your information. I think it is important for me and for another people. For me, talk about the AI vision of future work, that I see your movie have some women shopping online and have someone call to her and have a visualize in front of her. The question of my question is it for real or just a prototype? Because I think it's like a magic when I see the answer that I'm calling in front of me. The question is just now is a prototype or it can be real?
I think it's very feasible to build a system like that. You know, we have all of the technologies, so we have augmented reality headsets. You know, we have the algorithms to detect and recognize a huge range of objects, and we can also build applications where, you know, the context also gets triggered, and you know, if you're shopping, well, you know, this is the right like pet food to buy, not that one because we know our pets don't like it. This is where to find it. So all of that could be done. The issue at the moment is probably other things like privacy, you know. So what would stop Google Glass in part being used, and it worked quite well, was certain businesses didn't like people with the glasses coming in and just videoing everything, right? Because, you know, that they could like look at the window locks, you know, look where, you know, the fire door is, all of that sort of thing. And, you know, that would give intel for people to kind of misuse and do non-legal tasks. So I think the challenge is not so much the technology, although it would be difficult to get this kind of system working in a huge variety of spaces. But I think the bigger problems are really other problems, like the societal problems, privacy problems, and whether other stakeholders you like this. I think those are really the barriers. But yeah, thanks for your question.
Thank you so much.
There's one more question in the front from Ajahn Roy.
In the front, please.
Yes, good morning, sir. I'm Roy Morian from the Naresuan University Graduate School. We've seen with the COVID pandemic a significant loss of social contact and a significant growth in personal isolation. And this loss of social contact and personal isolation seems to have continued after the pandemic has kind of faded away. With this sort of architecture and AI, such as in the video that you were showing, what are the social implications of this in terms of social isolation and social contacts?
That's probably the hardest question that's been asked. I mean, it seems to me as though it's going to make the system worse, right? Having these kind of systems, because you know, for various like common sense reasons. I mean, one is you're like with this augmented reality application is you're so flooded with information that you need to like pay attention to. You're less likely to like socialize, you know, with anybody like sporadically and non-deterministically who are close by, right? So that's probably going to happen. And then if you get this richer interaction, right? So, you know, we could say that augmented reality, you know, could be linked to like virtual reality and you know, the metaverse and all of that stuff. Then that also means that we now perhaps feel more comfortable, you know, interacting with, you know, in virtual reality than we do in real, you know, reality. So our familiarity and our gain from physical sort of interaction, again goes down. So I do think it's like a real problem. And I'd be interested to know if I personally am not clear what would be useful solutions which AI could do, or how we could regulate these systems, or how service providers could reduce the social isolation. I don't have any great ideas on what to do there. And if you have them, I'd be interested to speak to you.
Another question?
Hi, Stefan. Very good talk. I appreciate your thoughtfulness and a lot of deep material. And I invite everybody to look carefully at every word that you've said. In particular, one person I remember from what I've studied is John Koza. The work he has some very interesting evolutionary computation, things like variation and selection, things like that. My question to you is, you describe very well the non-human aspects of autonomous models and such, but what can you say about the disconnected aspects of autonomous or autonomy in sense, when you have devices at the edge, IoT, you're beholden to a wireless or a non-reliable communication link, and the problem with wireless at the 2 to 10 gigahertz range, that's ionizing radiation. The pervasivity of the cell towers around that these devices are either distributed or centrally linked. There's some, well, I don't know, there could be some serious biological effects of the cancers from high levels of 10 watt, 20, 30 watt RF, millimeter wave stuff like that. And whereas what do you say about I see two types of autonomous agents, non-human and disconnected.
But by disconnected, you mean like disconnected from the physical world?
Yeah, totally self-contained, self-sufficient.
Yeah, we could ask people in the audience, right? Well, when do you think would be the time, right? You get into an autonomous vehicle, and it leaves, it arrives where you live, right? And takes you where you need to be, right? Your business or studying or somewhere. When will that be, right? 2 years' time, 5 years' time, 10 years' time. And then when that happens, we will become disconnected from the physical world, and we will use more digital interaction more and more, right? In these like autonomous vehicles. And then one of the other things that will happen is like our physical self will probably more likely deteriorate, right? Because we're not physically exercising during our daily commute, because this like autonomous vehicle is just so convenient, is good at spatial routing, arrives right close to us where we're leaving, and then puts us close to kind of where we need to be. So, I do think we're definitely becoming more digitally dependent, and we have a stronger disconnect from the physical world and from ourselves. And again, I find that worrying, and I don't really have any answers on what we could do to guard against that. It's a really serious problem.
Thank you for that. We have time for one more question.
One more question from me is that you talk about small data for AI models. How can we avoid bias to the data or overfitting to the data if we have like a small set of data?
So, I mean, I suppose there's like several ways. I mean, one clear way is to like do enough observations. So for example, that traffic light database that they have, they basically collected 3 days of traffic light data, and I'm not sure how many traffic lights they had. Was it like 4,000, something like that? And they collected it day and night time, and they collected it in different weather conditions as well. So you could say that if you design your data collection the right way, and you could collect a small amount of data, providing you captured the kind of like the characteristic, like varying conditions, in the environment. So that would enable you to like collect a small amount of data. I mean, the other thing, right, is if you choose particular types of users, some users would give you like better quality data than others. So you could have, if you target the right users, you could also get a smaller, better data set than if you had more users. More users might give you more noise, right? And too much variability, which then you'd be caught in between. You'd really need a big data set, right, if you had this. So you'd have to look at how much is the environment varying, and how much is the person who's interacting in the environment doing things in different ways, and then based upon that, determine how big your data size needs to be. And I mean, as we said, it's like very hard, right, to generalize that. So we could collect a small data set in a particular like environment, but it would be unclear so far how effective that would be in like another environment, right? So we might, if we spotted that the environment's changing, we probably have to collect more data. But it's a very good question, and there's no easy answer.
Thank you very much.
Right. Thank you very much for all the questions, and thank you, Dr. Poslad, for your talk. We have learned about how big data is big data, and all the distributed AI with IoT edge devices, and also how to design small AI, right?
I really enjoy it as well. So we would like to invite Dr. Sanya Krihong to present Dr. Poslad with a gift to show our gratitude. Please, Dr. Sanya Krihong. Okay, please give a big round of applause.